A moderate earthquake directly beneath Seattle could shake the city harder than a magnitude 9 100 miles offshore. That is not a hypothetical. A shallow fault runs straight through the metropolitan core, and about 1100 years ago, it threw the shoreline more than 20 feet into the air and sent a tsunami across Puget Sound. New research now suggests it may rupture more often than the hazard maps assume. Everyone here is watching the ocean. By the end of this, you'll know why they should be looking down. There is a fault running directly underneath the city of Seattle, and almost no one is looking at it. For decades, the entire conversation about earthquakes in the Pacific Northwest has pointed in one direction offshore, out to sea, toward the Cascadia subduction zone and the magnitude 9 megathrust that everyone calls the big one. That threat is real, and it earns the attention it gets. But while the public stares out at the ocean, a different fault sits in a far more dangerous spot. It does not sit 100 miles offshore. It runs straight through the middle of the city. The Seattle Fault is a shallow crustal fault, and that single fact changes everything about how it behaves. It is not the deep offshore megathrust people picture when they think about the big one. It strikes roughly east to west across the Puget Lowland, and it passes directly beneath downtown Seattle, beneath the stadiums, beneath Bainbridge Island and Bellevue, and the southern shore of Lake Washington. It is a reverse fault, a thrust fault, where one block of crust is shoved up and over another. And it is not one clean break. It is a zone of multiple parallel strands, part of a larger family of shallow faults beneath the region that also includes the Tacoma Fault and the South Whidbey Island Fault. Here is why that matters, and why it should change the way you think about earthquake risk in this city. When a fault is this shallow and this close, there is almost no distance for the shaking to weaken before it reaches the surface. The energy is born just a few miles down and arrives in the streets above almost immediately, at close to full strength. A fault directly under a city of millions does not need to be enormous to be catastrophic. It just needs to move. To understand the threat, you have to understand a counterintuitive truth about earthquakes. Bigger is not always worse for a given city. What matters just as much as the size of the quake is how far you are standing from it, and how deep it is. The Cascadia megathrust is genuinely massive, capable of a magnitude 9. But it lies offshore, tens of miles to more than 100 miles from Seattle, and the rupture happens deep beneath the seafloor. When that fault finally goes, the seismic energy has to travel all that distance through the crust before it reaches the city, and along the way it spreads out and weakens. Seattle would still shake hard, and it would shake for a long time, several minutes of rolling motion. But the most violent, most destructive ground motion from a Cascadia event happens out at the coast and offshore, not in the city itself. The Seattle Fault flips that entire equation. It lies directly beneath the urban core, at a rupture depth on the order of 12 to 13 kilometers, roughly 8 miles straight down. A rupture on this fault would be smaller in total energy than a Cascadia 9. We are talking about a magnitude in the range of 6.5 to 7.5. But because the source is right underneath the buildings, the bridges, and the buried gas and water lines, the peak ground acceleration delivered into the city can actually be more severe than what a distant magnitude 9 would produce. The violence arrives with no warning and no travel time to soften it. This is the part that gets lost in the headlines. People hear magnitude 9 and assume the bigger number is automatically the bigger danger to Seattle. But total energy released is not the same thing as how hard a specific place gets shaken. A moderate quake directly underfoot can hit a city harder than a giant quake far away. And the Seattle Fault is about as underfoot as a fault can get. Consider what a magnitude 6.5 on this fault would mean in practical terms. The United States Geological Survey actually models that exact scenario, a magnitude 6.5 on the Seattle Fault, and they model it precisely because it is realistic and because the consequences are severe. A quake that size, centered under the city, would last only a matter of seconds rather than the minutes of a Cascadia rupture. But those seconds would be brutal. Older brick buildings, unreinforced structures, elevated highways, and the bridges that stitch the region together would take the full force of the motion before anyone could react. The duration would be short, but the intensity at ground level would be extreme, and it would be concentrated exactly where the city is most densely built. There is a second factor that makes the ground beneath Seattle especially dangerous, and it has nothing to do with the fault itself. It has to do with what the city is built on. Seattle sits on top of a sedimentary basin, a thick bowl of soft, loose sediments filling in the bedrock beneath the surface. When seismic waves hit soft sediment like that, they slow down and pile up, and the basin can trap them and bounce them around, intensifying and prolonging the shaking. Seismologists call this basin amplification. It means the same earthquake will shake a neighborhood built on soft basin fill far more violently, and for far longer, than a neighborhood built on solid rock nearby. If you want to know how dangerous that effect can be, look at what happened in Mexico City in 1985. A massive earthquake struck hundreds of miles away on the coast, and yet the worst destruction happened in the capital, far from the epicenter, because the city sat on an old lakebed of soft sediment that amplified the waves into something monstrous. Distance should have protected Mexico City. The basin erased that protection. Seattle has its own version of that bowl, and a moderate quake on the Seattle fault would pour its energy straight into it. The shaking could be amplified well beyond what the raw magnitude would suggest, concentrated exactly where the most people and the most infrastructure are. This is the force multiplier that turns a moderate crustal earthquake into a city-breaking event. So how worried should you actually be? This is where the story demands honesty, because there is a version of this topic that is pure fear, and there is a version that is true, and they are not the same. The fault's destructive power is not a theory. Geologists have documented, in detail, a major earthquake on the Seattle fault that struck in the winter of the year 923 to 924, roughly 1100 years ago. That event has been estimated at about magnitude 7.5. We will come back to exactly what it did, because what it did is staggering. For now, hold on to the date. 1100 years ago. Now here is the nuance that separates the truth from the hype. For the very largest earthquakes this fault can produce, magnitude 7.5 and above, that ancient event appears to be the only one in roughly the past 11,000 years. That tells us the recurrence interval for the maximum size Seattle fault earthquake is likely no shorter than about 5,000 years. In plain terms, the absolute worst-case quake on this fault is not statistically overdue. Anyone telling you the big one under Seattle is due tomorrow is overstating the case. But there is a second clock, and this one matters more. For moderate but still devastating earthquakes magnitude 6.5 and above the geologic record shows, the Seattle fault has been active 3 to 4 times in the past 3,000 years. That works out to an earthquake of about magnitude 6.5 or greater, roughly every 1,000 years. And the last major rupture was about 1,100 years ago. On that clock, the moderate event, the one that is, frankly, the more realistic threat, is the one that is plausibly due. Not scheduled, not predicted for a date, but due in the geologic sense, and sitting directly beneath a city that has grown to millions of people since the last time this fault moved. The story would already be serious if it ended there, but it does not end there, because the picture has gotten worse in the last year, not better. New research circulating in 2026 indicates that the network of shallow faults beneath the Seattle area is more complicated and more active than the official maps account for. There appear to be hidden, secondary fault strands beneath the region that are not represented in the National Seismic Hazard Model, the very model that engineers and planners rely on to decide how strong a building has to be. If those strands rupture more frequently than anyone has been counting, then the real hazard under the city is higher than the official numbers say. There is a second finding that is even more unsettling. The research suggests that 2 Seattle area faults may have ruptured at about the same time in the past. That raises the possibility of a linked, compound rupture, 2 faults failing together, or in quick succession in a single seismic event. If the Seattle fault and an adjacent structure like the Tacoma fault can go together, the footprint of severe shaking across the Puget lowland could be larger, and the shaking could last longer than any single fault scenario predicts. This is the core of why this story matters right now. We are not just talking about an old fault with a long history. We are talking about a fault system that the standard hazard maps may be underestimating, beneath one of the fastest growing cities in the country, at a moment when scientists are actively revising upward what they think it can do. The threat is real, it is close, and it is partially invisible to the maps we have been trusting. Think about what it means for a fault to be missing from the official model. Building codes, insurance assessments, retrofit programs, emergency planning, all of it is calibrated to the numbers in that hazard map. When the map says a certain level of shaking is the worst a neighborhood needs to plan for, that number becomes the standard a new building is engineered to survive. If the real shaking could be stronger or more frequent than the map assumes, then some of the structures going up across Seattle right now are being built to withstand a quake smaller than the one the ground beneath them can actually deliver. That is the quiet danger of an undermodeled fault. It is not just that the science was incomplete, it is that the incompleteness gets poured into concrete and steel, and it stays there for the life of the building. To understand what this fault is capable of, you do not need to imagine anything. You only need to look at what it already did. In the winter of 923 to 924, the Seattle fault ruptured in an earthquake of about magnitude 7.5. The best-fitting model from the United States Geological Survey describes an oblique reverse slip running southwest to northeast, with roughly 15 meters of horizontal shortening and a ruptured depth of about 12.5 kilometers. Those are the dry numbers. What they produced was not dry at all. At Restoration Point, on the southeast tip of Bainbridge Island, the land was lifted straight up by roughly 7 meters, about 20 to 23 feet, in a matter of seconds. A piece of the shoreline that had been at the water's edge was thrown 20 feet into the air and left there. It is still there today. You can walk on it. It is a slab of former seafloor, now sitting well above the tide line, a permanent, physical monument to a single earthquake. Across the water at Alki Point in West Seattle, the ground was uplifted too, by as much as roughly 20 feet. When the seafloor of Puget Sound rose like that, it shoved the water above it, and the water had to go somewhere. The result was a tsunami inside Puget Sound itself. This was not a wave from far out at sea. It was generated right there, in the enclosed waters of the Sound, and it swept across them. Geologists have mapped the deposits that tsunami left behind, and they reached the site of what is now the West Point treatment plant. The same fault that lifted the shoreline 20 feet also sent a wall of water across the Sound, and it did both in the span of a single event. The shaking did something else that winter, something almost eerie in how well it has been preserved. It sent a massive landslide crashing into Lake Washington. When that slope failed, it carried entire stands of living trees down into the lake, and those trees did not topple over. They slid in and stayed upright, rooted in the slumped ground, and they came to rest, standing on the lake bottom. They are still standing there now, more than 1,000 years later, submerged groves that divers and sonar have found beneath the surface of Lake Washington. Scientists call them the sunken forests. They are, in effect, an underwater timestamp, a stand of trees frozen at the exact moment the Seattle fault last moved. The landslide may even have generated its own secondary tsunami within the lake. These are not legends or estimates. The uplifted point you can stand on, the tsunami deposits you can dig up, the drowned forest you can find on the lake floor, these are concrete, physical, datable records of what this fault did the last time it ruptured, at full force. And every one of them points back to the same uncomfortable fact. The fault that did all of this is still there, beneath the same ground. Except now that ground is covered by a metropolitan area of millions of people, with highways and high-rises and bridges and pipelines that did not exist 1,100 years ago. That is what makes the ancient quake so important. It is not history for its own sake, it is a preview. It is the clearest possible answer to the question of what the real threat looks like when it actually happens. And it is sitting in the geologic record, waiting for anyone willing to look. None of this means the Cascadia subduction zone is a myth, and it is worth being clear about that, because the two threats are often confused. Cascadia is the offshore boundary where the Juan de Fuca plate dives beneath North America, and it is fully capable of a magnitude 9, an earthquake hundreds of times more energetic in total than a magnitude 7.5 on the Seattle fault. When Cascadia ruptures, it will be one of the largest earthquakes this continent can produce. it will shake the entire region for minutes, and it will send a tsunami racing toward the outer coast. It is a genuine catastrophe in waiting, and the attention it receives is not misplaced. But here is the contrast that sharpens the whole story. Cascadia's fame is exactly why the closer danger goes unwatched. The public has been trained for a generation to look out to sea, to picture the offshore monster, to brace for the wave on the coast, and in doing that, it has stopped looking down. The energy from Cascadia has to cross all that distance to reach Seattle and weakens on the way. The energy from the Seattle fault is already in the city. Per unit of magnitude, delivered to Seattle specifically, the fault under the city is the more dangerous of the two, not because it is bigger, but because it is closer, shallower, and sitting on top of a basin that will amplify whatever it produces. So, the honest framing is not that Cascadia does not matter. It is that the region has been watching one threat so intently that it never noticed the other one was directly underfoot the entire time. Whenever this fault comes back into the news, a predictable set of claims comes with it, and they are worth addressing directly, because the truth is more useful than the myths. The first claim is that scientists already know exactly when the next quake will hit and are hiding it. That is simply not how any of this works. No agency on Earth can predict the date, time, and magnitude of an individual earthquake. What hazard science can do is forecast probabilities and identify the zones that are primed, and that is what is happening here. Scientists are not concealing a countdown. There is no countdown to conceal. There are only areas of concern, and Seattle is one of them. The second claim is that the gap between the official hazard maps and the newly mapped hidden faults proves some kind of cover-up. It proves the opposite. That gap is exactly how science is supposed to work. New faults get found, new research gets published openly, and the maps get revised to match reality. The fact that the model is being updated is a sign the system is functioning, not failing. The third claim is the most seductive and the most important to correct. People hear that a quake is overdue, and they translate that to imminent. But due on a 1,000-year geologic clock does not mean due tomorrow. It means the risk is real, persistent, and badly underappreciated, not that you should expect it this week. The danger here is not a date. The danger is complacency about a fault that has every capacity to break the city and a public conversation aimed in the wrong direction. So where does that leave the millions of people living on top of this fault? It leaves them with a clear, practical picture, and that clarity is the whole point. The Seattle fault is not a doomsday clock ticking down to a fixed hour. It is a shallow, close, capable fault with a documented history of throwing the shoreline 20 feet into the air, drowning a forest, and sending a tsunami across Puget Sound, and it sits directly beneath a city that has never experienced one of its ruptures in modern times. The moderate magnitude 6.5 class event is the realistic threat. It recurs on a roughly 1,000-year cycle, and the city is past the last one. The new research suggests the hazard may be higher than the official maps show, and that hidden strands could even rupture together. What should you watch for? Watch the hazard models. Because as the 2026 research works its way into the official maps, the expected shaking for Seattle is likely to be revised upward, and that will reshape building codes and retrofit priorities. Watch how the region invests in preparing the structures that matter most, the bridges, the older brick buildings, the utility lines that a shallow quake would tear through first. And understand the threat for what it is, because that understanding is the single most valuable thing you can carry out of this. The real danger under Seattle was never only the famous one offshore. It is the quiet one underneath, the one that has already shown us exactly what it can do, waiting on a clock the city has nearly run out. The science is telling us where to look. The only question left is whether we finally look down.